right, welcome everyone. My name is Justin Clark. I'm a root cause analysis instructor with Taproot, and I also run the equipment reliability program called Equifactor. This is our troubleshooting techniques. This is a module within Taproot root cause analysis, and today we're going to be talking about 3 ways that you can improve your equipment reliability today. There's 3 major concepts we're going to be touching on. We're going to talk about reactive discipline and how to walk through an equipment failure and troubleshooting, how to proactively prepare for equipment failures to make that process as easy and as intuitive and as structured as possible, and then we're going to talk about how to do good root cause analysis to get rid of everything that allows equipment to fail. So one of the first things we want to think about is how can we discipline the process of reactive equipment troubleshooting? The first thing we want to think about is what is our normal process if we have, let's say, a major alkylate explosion in our oil refinery. It's going to be maybe a brainstorming, getting together, figuring out, okay, what can we go to fix? And normally our priority is going to be how can we get operations back online as soon as possible. And while we might return the equipment to a running condition, we start our process again. Our priority might not necessarily be fixing the root causes or fixing what allowed the equipment to fail. It's naturally getting operations back online. And so if we don't go find the root causes, we're leaving a vulnerability in our system for a repeat failure. If we don't go in and prove exactly what happened, we're never going to be able to prevent it from happening in the future. So the late Heinz Block has an excellent quote about equipment troubleshooting. He would say that in all cases of equipment failure occur to a succession of oversights. There's never just a single point failure. Every single one happens due to multiple failed or missing safeguards. And you have to pay attention to these details that allowed the equipment to fail so you can understand why. You have to remove each of the vulnerabilities and the increase in risk due to each detail because you don't know which one is going to cause your equipment to fail. And so we need to do this thing called equipment troubleshooting. This is a term we use a lot, but nobody actually really specifically defines it. So we want to look at what equipment troubleshooting is not first. Equipment troubleshooting is not brainstorming. Equipment troubleshooting is not just replacing broken parts. Tear the pump out and replace it. Equipment troubleshooting isn't just getting the equipment back up and running. That's returning operations. Equipment troubleshooting is not apparent cause analysis. That term, apparent cause analysis, people use that when we don't care enough about what actually happened to go prove why it failed. Equipment troubleshooting is narrowing down all of the possible causes, developing a strategy to go prove and gather the rest of the information that we don't have, gathering that evidence with our strategy, and then proving exactly how the equipment failed. Because if we don't understand what happened, you can never understand why it happened. So a very, very wonderful man, Sherlock Holmes, once said, via Sir Arthur Conan Doyle, "You need to eliminate the impossible, and whatever remains, however improbable, must be the truth." Equipment troubleshooting is a lot like this. You need to go eliminate the entire universe of things we don't care about and only focus on what could have possibly caused this and then prove it. Elementary, my dear Watson. So we need an exhaustive list of possible causes. We need to eliminate what doesn't apply and what we've already checked. No self-respecting mechanic is going to let us get to a root cause analysis or a troubleshooting without having done a valve lineup or doing a clean inspect on the upstream strainer. And then we need to prove gather the evidence to prove what is left, the possible causes that remain. So here's an example of maybe a basic pump failure. We had a pump get removed from a system for an overhaul. We had both our predictive and preventive maintenance telling us this needed to happen. So it was due for an overhaul per the preventive maintenance schedule, and the vibration monitoring system told us that it's above specification. Our predictive maintenance also tells us, hey, we needed to pull this pump out. So we uninstalled the pump, took it to the shop for an overhaul. We got new bearings, impeller, and seals, as well as we did a complete balance on the pump. We reinstalled it, and when we did post-installation testing, it failed its capacity check, meaning it wasn't pumping enough fluid. So it failed at 30% below its rated capacity. So I want to take a minute, just think about if this is all we know, and in our normal process we get everybody together in a room to start quote-unquote troubleshooting, what are all the possible causes? Oh, maybe we didn't do a valve lineup. Maybe we didn't check the strainer. Maybe all of these things. And, you know, you might come up with a pretty good list. And one of the things you want to do is eliminate everything that it could possibly be. But if you don't know every possible cause, let's say your vibration analyst is out, if you don't know, or if you don't have your pump expert right handy, then you may not know all the questions to ask. And so one excellent thing to do to improve your equipment reliability is to beforehand get all of those questions together. Have all of the possible causes for that type of equipment. There's only so many ways a pump can fail. There's only so many ways a diode can fail. There's only so many ways a gas turbine can fail. And if you have all of those questions lined out, it's much easier to step through the process of determining what happened, because you know exactly what questions you need to ask. And so here's something of what that would look like. And just in our short little time here, we probably didn't come up with all of these. And even if we sat down in a room, you know, everybody, all the experts available, we might not come up with all of these because we're losing $300,000 a day and we're just trying to get operations back up online. So it's a tool. It helps to have all of these possible causes for that insufficient capacity, that pump capacity failure, already there so we can go eliminate. Boom, boom, boom. And here's the only 4 possible causes. So I want to challenge you, did you think of all of these? Probably not in the 10 seconds I gave you. Did you think of all of these just based off what you knew? Probably not. It helps to have that comprehensive list. So the next thing we want to do is everything that remains that we didn't already check or that we know doesn't apply to our system, everything that remains is a much smaller list. And so we can take maybe these 4 things that we found, and now we can structure an evidence-gathering plan. So again, we want to eliminate all impossible causes, determine the possible causes, and then go prove which one of these is the real cause. And naturally, you want to hit all the easiest ones first. If you don't have to take the pump out of the system, then obviously you don't want to do that. And then you want to make sure that you don't lose any data as you're doing your troubleshooting. If I tear apart my 24-cylinder diesel engine and I don't think to label the piston rings as I'm disassembling it, I just toss them all in a pile, all of that data on which piston ring went with which piston, and thus which piston was causing the problem, that one gets lost. So we need to just have a plan. We need to make sure we don't lose any of the data that could tell us exactly what happened. And so you want to have something like a troubleshooting strategy checklist, a sequence that tells you, okay, for these symptoms and these possible causes, here is where we need to find the data as early as possible so that we don't lose it. And then, when we hand this list to our equipment troubleshooters, we can feel confident that that we're not just going to miss steps. And so let's say for this insufficient capacity, there's only so many places we need to check for data. Here's these possible causes we found. Our impeller diameter was too small. It was installed, the impeller itself was installed backward, and there might have been an obstruction. These are the things that we couldn't prove or that we didn't already check without tearing the pump apart. And so building our plan to troubleshoot, there's things we want to do before disassembly. Can we check the impeller orientation? You know, if you tear the pump apart and have all your pieces laying there in front of you, you're going to lose the data on which way the impeller was installed. And also, when you pull the pump out, make sure you check your piping. Then you want to make sure you go back and measure your impeller diameter and verify that as you're going to be putting it back together that you are putting it in the right spot. And this is where you would be gathering things like, are there rotation markings on the impeller? Is there a little etched in thing that says this side up, this side down, that may help or that may indicate whether or not it is installed incorrectly? And then you want to go back and do your operational capacity tests after you put it back together to make sure we didn't introduce any other errors. That's the most common reason machines fail, is that we do maintenance on them. We want to make sure we don't introduce other errors. As we're reinstalling it, we want to make sure we're checking for blockages in piping. And then finally, once we get it back in the system, we want to make sure that we didn't do anything else that caused another problem. And so we want to be disciplined about our troubleshooting. Eliminate the not applicables and low-hanging fruit first. You probably don't need to get to a structured troubleshooting plan if it's just simply a valve lineup issue. This is for those situations where we're tearing our hair out and we can't figure out what's going on. Then you need to structure and strategize your evidence collection so that you can gather all of the data and prove exactly what happened. And then obviously don't lose your data. Make sure you capture it as early as possible because some of those things might go away. So this leads us to, okay, that'd be nice to have all the questions to ask, but let's say I don't have my list. Well, shocker, no brainer. Maybe you need to build a list so that as much as you can beforehand, you're thinking out your troubleshooting process. And so you want to build something like that list of possible causes so that you have your troubleshooters don't have to think of all these things on the fly and risk forgetting certain questions to ask. So to build one of these lists, use your subject matter experts. You want to be consulting with your engineers, your operators, your manufacturers, all those machine whisperer guys that have been running old Bess for 30 years and know all of the things to do that aren't necessarily in the procedure. You want to ask and work with other companies. Maybe your company hasn't experienced this particular problem or this symptom before, but chances are somebody else in the world has. And so you want to start developing these comprehensive tables and guides to help your experts troubleshoot effectively under stress. Because remember, we're not just doing this in a vacuum. We're losing hundreds of thousands of dollars a day or an hour because our operations aren't back online. This isn't exactly a comfortable environment. So we want to make it as easy and intuitive to find the right answer the first time. So there's 3 levels of proactivity that we want to go through to make sure that we make this as easy and as fluid as possible. First, you're probably familiar with what's called a failure modes and effects analysis. Going and thinking through what are all the ways that my equipment can fail. You want to use this to plan your troubleshooting before the equipment fails so that you know exactly what to look for in each circumstance. Because again, how many hundreds of thousands of dollars an hour is your operations worth? Every minute that you can save in an unplanned outage is worth many, many, many man-hours or many, many, many dollars in time spent pre-planning. It is always going to be worth it. And the goal is to guide the maintenance teams, the corrective maintenance teams, and the emergency responders, and our reliability teams give them what they need to do it as quickly and efficiently as possible, and that's how we get operations back up online with first-time fixes that we know will not happen again. So that's level 1 proactivity. Level 2 proactivity is, so now we know each possible cause for each symptom. Once we've developed that holistic list, that comprehensive list of questions, now we know every way that it can fail. Now we need to design systems around each of those failure modes to prevent it from happening, or to make it unlikely that it will happen. And so we know that maintenance is never trumped by, or maintenance is always trumped by operations, but the best practice and the best-in-class performers never let operations defer maintenance. I don't have time to fix my equipment, I have to run my equipment. It's kind of the normal mode and habit we fall into. But what that buys us into is an unplanned outage, an unplanned turnaround, unplanned tearing the equipment apart and trying to figure out what happened. And so during our turnarounds, we need to make sure that we schedule enough time to actually complete the maintenance. That sounds like a no-brainer, but these things happen way more often than you would think. So you're always going to buy equipment maintenance either with turnaround days or with operational days. The turnaround days, when the equipment is already offline and it's not running, buying your fixes with those days is much, much cheaper than buying them with operational days. And it's much safer. Unplanned outages are usually pretty painful and always expensive and dangerous. So that's level 2 proactivity. Level 3 proactivity is know the state of every piece of equipment that you have and whether or not it's feasible or a good idea or profitable to upgrade. Here's another Heinz Block quote that's pretty heavy-hitting for our reliability-centered maintenance crowd. Investing in a procedural, reliability-centered maintenance program before implementing effective upgrades is both costly and unproductive. Monitoring things is not very productive or profitable if your equipment is just that vulnerable. And so reliability-centered maintenance efforts are wasted if your plant hasn't yet implemented what best-in-class performers have already proven to be good ideas. Maybe we're still using oil fling rings instead of, let's say, oil mist lubrication. These things may be good for low-quality, low-performance pumps, but if you're wanting any kind of reliability, you need to start moving away from these things and implementing best practices. A plant that isn't implementing the basics of sound maintenance is never going to benefit from reliability-centered maintenance programs. So, parts and equipment that are subjected to wear and other life-shortening events only exist in plants that refuse to implement known upgrade measures. And so what we want to do is look at the best performing plants and realize that their equipment doesn't really wear out. Their equipment doesn't break down. Their equipment continues to run and purr and hum along, and they never have these painful unplanned outages because they prevent them. So, we need to move into this next step of, okay, we have an equipment failure, we dealt with all the technical things, and we were able to replace the part and get operations back up and running, but we still need to learn many lessons about what in our system allowed this problem to happen. And so rather than just asking why, we want to ask something more targeted and more specific. What systemic problem allowed this equipment failure? First key concept in root cause analysis, good root cause analysis, is that blame and discipline are useless to prevent future similar accidents. And then we want to figure out what we can do better as a business and that we have the power to fix. So this is targeting a little bit about what root cause analysis is trying to get at and what good root cause analysis finds. So just like with equipment troubleshooting, there's a lot of things that root cause analysis is not. Root cause analysis is not brainstorming. It's not guessing. It's not blaming the people involved. Saying that there's a human error is not root cause analysis. That should be the start of your investigation, not the end. Identifying equipment symptoms is not root cause analysis. Identifying that a human made an error, again, that's not root cause analysis. That is something that happened that has probably many root causes. Finding what part broke or what impeller was installed backwards is not root cause analysis. That's simply understanding the symptom. Because if I run my car into a tree, it makes a huge difference whether or not I was driving under the influence or if my brakes were not functioning. There's different root causes there, and there's different things that allowed each of those to happen. And again, apparent cause analysis is not root cause analysis, because ACE is simply saying I don't care enough about the severity of this incident to prevent it and prove what happened. So root cause analysis is, first, collecting evidence and understanding what happened based on that evidence, identifying the critical path to failure, all of those oversights, all of those missing best practices, all of those failures to apply knowledge, and then proving those root causes using the evidence for each of those missing safeguards, for each of those failures to apply knowledge. And so we hear root cause, that term, out there almost every single news feed that you get into. But it's one of those terms that is not very well defined many places that can really send us in a good direction once we have a proper definition. So, an excellent definition for a root cause, what we're trying to get at with root cause analysis, is the absence of a best practice or the failure to apply knowledge that would have prevented the problem or significantly reduced its likelihood or consequences. And so just thinking about that definition there, that tells you this is something I can go fix today. This is something that I can take action on today and change what I am doing as a company to make sure that this type of problem doesn't happen again. And it's focused on improvement. It's not focused on blame. It's not focused on discipline. It's focused on how can we prevent this accident from happening again. And so as you're doing a root cause analysis, whatever system you're using, it needs to be structured. If you just put a whole bunch of people in a room with a piece of paper, it's probably not going to happen very easily. And it's going to be very painful, unstructured, and it's going to take much longer than it needs to. And so there needs to be a path to tread. It needs to be guided. We want to make sure that we have as many of those questions to ask as possible so that we don't miss anything. It needs to be standardized. People need to know what to expect when they're walking into an investigation. The worst thing you could do is just say, go investigate and do good things. But if there's no training, if there's no structure, if there's no process that's standardized, if you hand that process to different teams, they're going to get wildly different answers based on their opinions, their experience. It's very subjective. And so you need to have a standardized process. And finally, it needs to be evidence-driven. All those questions that we're asking need to be answered with the evidence. Because if you don't have these four things, structured, guided, standardized, and evidence-driven, Your results won't be actionable. You can't fix human error, but you can fix something like labels need improvement and training objectives need updated, or my computer displays need a different format. Displays need improvement. It needs to be objective so that you can justify every change you're making. And if it is these things, then it becomes very easy to trend and very easy to see where our repeat root causes are coming from. And then finally, at the very end of things, we want to be able to defend ourselves if any kind of legal action gets brought against us and prove how we eliminated these problems step by step using the evidence. So here's maybe one thing that we found for that pump failure. The mechanic installed the impeller backwards. That's not a root cause. That's a mistake that was made that has probably many root causes. And when we went and did this investigation, we found that there were quite a few. There was no procedure for this pump overhaul. On our quality control side, there was no hold point to make sure that we installed the impeller in the proper direction. For a human-machine interface, there was no label to say this end up, or make sure it's rotating this way. For the work direction side, we found that the team selection needs improvement. This was a freshly qualified mechanic that had never performed an overhaul even in training. And also there was no supervision that we found. And so you can see that there's many things that allowed this one mistake, this human error, to happen. So there's usually never just one root cause. There are many root causes for each mistake that led to the failure. And so think about something like a major oil refinery explosion. We identified 6 mistakes, failed safeguards, or missing safeguards that led up to multiple alkylate explosions. And so we're going to walk through an exhaustive root cause list of everything that we found. Actually, I'm just kidding, we're not going to do that. I will let you know that for this particular incident, just from a CSB report, we didn't investigate this ourselves, just from the report, we found 16 unique root causes, and there were 5 of those that repeated. And so you can start to see how a simple equipment failure, maybe some of these lockout tagout issues that keep happening, maybe a repeat equipment failure for our mechanical seals, many of these things have multiple root causes, many ways that we can better our business practices to make sure that they don't happen again. And if we would have gotten rid of any one of these mistakes, errors, or failures, this incident wouldn't have happened. So there are many opportunities to improve, and this is how you target your continuous improvement program that isn't just this nebulous, hey, we need to get better type of thing. And so these are missing best practices that we need to assimilate. So that was a very quick run through on 3 ways to improve reliability. You need discipline in your reactive equipment troubleshooting. You need to learn lessons from that, and as much as you can beforehand, be proactive to prepare for when your equipment fails. And then you need to do good root cause analysis because, sorry to say it, engineers, humans are involved in running, operating, designing, maintaining equipment, and you need to understand how to properly deal with them. And so then, at the very end, building equipment reliability means removing everything that allows your equipment to fail. There is no monitoring, there is no system to keep track of the health of our machines that will prevent them from failing. But, like we saw earlier, the basics of good maintenance, upgrading when it's feasible, and a best practice are the foundations of how to improve equipment reliability, and pursuing that low-hanging fruit is a much better use of your time than implementing reliability-centered maintenance if you don't already have those foundations. So, like we saw earlier, best-in-class performers don't see equipment wear out because they've done what it takes, they've developed the discipline and the structures, and they've upgraded where they need to make sure that stuff doesn't happen. And so now what? What now? That's a nice webcast, Justin, but But how? What do we need to do? How can I start doing this? Well, think about coming to an Equifactor course. Over 3 days, we go over every step of this process so that we can build these structures and make it easy and intuitive and objective, evidence-based, legally defensible, and really at the very end of things, financially viable to get operations back up and running as soon as possible. So I hope you enjoyed this webinar. I hope this sparked some good conversations in your company. If you have any questions, feel free to give us a shout out. I hope you have a great day.